Welcome to our presentation on the GAIA-X True Demand ecosystem. I'm Philipp Ulrich from Infineon Technologies AG, and I will present this demonstration today together with Schubert from the MSG Systems AG. We will start with a small motivation to our use case. Afterwards, we will talk about the characteristics of the semiconductor industry and especially the Bullwhip effect. We'll then go into our solution approach, which is the True Demand ecosystem, and follow this up with a demonstration of the system. We'll then conclude it and have a small summary of our whole use case. We will begin now with the motivation to our use case. Semiconductors are crucial to solve modern-day challenges, such as decarbonization and digitalization. Future mobility applications are mostly driven by semiconductors. For example, the rise of the electric vehicle market highlights the importance for having efficient batteries, motors, and overall efficient electronics for faster charging and longer driving ranges. On the other hand, automated driving systems in cars are becoming increasingly more complex, requiring sensors, microcontrollers, and more. Car-to-car communication, as well as smart cities interacting with vehicles, also heavily depend on IoT systems. And the green and efficient solutions we also need to act on the climate change. So overall, semiconductor supply is an important enabler for future mobility applications. Let's now talk about the semiconductor industry characteristics. Semiconductors have a long production times of more than 4 to 6 months. You can see here an example of a radar sensor on the right-hand side. Also, semiconductors are built in layers, making parallelization of the process steps on the substrate impossible. So you can see this here on the right-hand side on this little image. You have a hair for comparison to the tiny structures on a semiconductor, and you can see it is built in layers. So you cannot build the upper layers before you build the layers on the bottom. Also, building new fabs for increased production takes years and is also really cost and resource intensive. It costs more than €1 billion per fab. So overall, these characteristics restrict our flexibility in reacting to short-term demand changes. So we need accurate forecasts to plan our production for the automotive industry to enable future mobility applications. Let's now talk about a phenomenon that impacts supply chains heavily, the so-called Bullwhip effect. A phenomenon called the Bullwhip effect amplifies variations of demand heavily across the semiconductor and automotive supply chains. You can see on the left-hand side a small supply chain. You have the OEMs, which are the car producers that are getting their parts from the Tier 1 suppliers, for example, radar modules or batteries. And then you also have the Tier 2 semiconductor tier. They, of course, are supplying the Tier 1s with the semiconductors. You can already see that the Bullwhip effect is increasing from the right-hand side to the left-hand side. So it is increasing going to the Tier 2 semiconductor players. You can also see this here on the right-hand side in the simulation model. In the simulation model, you can see that the green line, which is the OEM, has a little bit of a demand drop, but afterwards the demand is recovering quite quickly. The red line, the semiconductor industry tier, has a really strong Bullwhip effect. So the line is dropping quite a lot and then going up again. And you can already see this whip here from the Bullwhip effect in this little diagram. As shortages grow, buyers seek to guarantee their own supply by ordering more than what they actually need, which we call tactical demands. And this amplification of demand intensifies across the entire supply chain, leading to shortages of chips and disrupting supply chains worldwide, affecting future mobility, digitalization, and decarbonization negatively. So what can you do against this Bullwhip effect? We will now talk about our true demand ecosystem as a solution approach for the Bullwhip effect. The Bullwhip effect can be mitigated by having more transparency and communication within supply chains. So this is exactly what our use case will cover. We implement surveys that can help automotive semiconductor supply chains to exchange information on demand, inventory, and trends more easily. We also want to remove the incentive for tactical demands with a completely anonymized survey to avoid tactical ordering and high demand variations. And finally, the survey outcome then will be used for analysis and decision making within supply chains. You can see this here in this little flow chart. There are some supply chain participants, for example, OEMs, Tier 1s, participating. They will give the information about demand and inventory into the multi-party computation survey that will analyze everything and average and aggregate it. And then we will get survey results as an output. GAIA-X will help us with this use case because it helps us to identify and register all the industry survey participants. It will also make the sharing of survey results and models within a market ecosystem possible, and it gives us standards for policies, contracts, data, and services. We'll now look into the architecture of the true demand ecosystem. We do have the supply chain, of course, with some examples from our own project. We have Infineon as an example for semiconductor player. We have Continental as an example for Tier 1, and we have BMW as an example for an OEM. Then we of course have the GAIX True Demand ecosystem with the anonymous multi-party computation surveys. All of the tiers would then participate within this anonymous multi-party computation surveys in input, demand, and inventory data without any way to find out what all of the others have been inputting. We would then be getting out the survey data, and of course we would have some analytics services so that we can use, reuse, analyze the data that we get out of the system and then make decisions accordingly. We'll now jump into the demonstration. I will now walk you through the demonstrator from the user perspective in a flowchart. First of all, we need to have a third party that is independent of the supply chain that can come up with a question catalog and then create a survey from this question catalog. The third party then invites known participants, for example, the OEMs, the Tier 1s, and the semiconductor manufacturers, in this demonstrator just via an email and a participation link. Afterwards, the third party can start the survey period and each participant has some time to fill in the survey, which they then do as a next step. After we finish the survey, the third party closes the survey and executes the multi-party computation to anonymously aggregate the surveyed information about demand and supply. Then the results are registered and uploaded as safe descriptions to the GAIX federated catalog. And the supply chain participants on the other side can now find and filter the survey results on a marketplace and discover everything that has happened in the past. We can then, of course, also initiate a data transfer of the survey results via the marketplace. And then there will be a data transfer done via the Eclipse database connector to get the actual files. For demonstration, let's now assume that we already have a third party that did create a survey beforehand, and the survey was already started and supply chain participants were invited to participate. We will now specifically look at a supply chain participant who is now filling in the survey via the anonymous survey service. We're now looking at filling in the survey from the point of a semiconductor manufacturer. We already got sent a custom participation link from the third party before, which we followed to this page. The current implementation of the survey offers a web interface in which you can input your data. Submission ID and participation code are already pre-filled from the invitation. We can now participate in the survey by clicking the button. One can upload an Excel or CSV file with the answers to the questions, as well as using the web interface. For simplicity, we will use the web interface today to fill in the survey. After clicking View Your Data, one can see all the different questions that are specific to your tier in the supply chain. For example, an automotive OEM would have questions on the development of the light vehicle sales. Since we are filling in the survey as a semiconductor manufacturer, we need to forecast the development of radar transceivers, which are important for electric vehicles and automated driving. We will now input our forecast for the development of the radar transceivers. To save time for the demo, we pre-filled all the other questions already. The other questions are about how semiconductor manufacturers expect the vehicle market to develop split in combustion engine and electric vehicles. After we check that all the questions are sufficiently answered, we can scroll all the way to the bottom and submit our input. The survey is now sent to the servers. Other semiconductor manufacturers will fill in the survey in the same way as other parts of the supply chain, like Tier 1 or OEMs in automotive supply chains. Questions within the tiers of the supply chain do have an overlap, but will also differ. Let's now jump to the viewpoint of the third party that closes the survey and executes the multi-party computation to anonymously aggregate the surveyed information about demand and supply. We're now looking at the survey management interface from the view of the third party. The third party itself is not participating in the survey and is managing and hosting the surveys, being independent from the supply chain. We now got the input of several participants from different parts of the supply chain in the time frame the survey was opened. We can now see that we got 3 responses to our survey from the semiconductor manufacturers. The next step is to evaluate the inputs according to the multi-party computation. The multi-party computation averages the input of all the participants, but we cannot trace back what each individual company did input into the survey. We now click on Stop to stop the currently running survey and then head over to Unmask. We now need to provide a PEM key, session ID, and password of the survey, which will start the multi-party computation evaluation. After the multi-party computation finished, we will get the aggregated survey results and can then download them for this demo to the local hard drive. The survey outputs statistics on usability, averages, and standard deviations of the input data. With this done, I now would like to hand over to Robert, who will guide you through the next steps within the GaiaX architecture.
Thanks, Philipp, for closing that survey and generating all that data for us. I'm Robert, and I'm here to show you how to get this data into a GaiaX-based ecosystem to be able to transfer this data from participant to participant. In the first step, we need to create self-descriptions out of our data and upload the self-descriptions in the federated catalog. Before I start to show you how self-descriptions are created, I wanted to show you a mapping from our use case in a functional matter to an architectural view, which is showing all the components that we need to fulfill our use case. So in the first step, our data provider needs to define its data, which he is able to do with the help of schemas. Schemas are ontologies and shackle shapes, and they have to be registered in the federated catalog. So every time a self-description is uploaded into the catalog, these are checked against the schema, and only if they are valid, the data is stored in the catalog. Moreover, every provider has to operate an EDC, which has an associated storage, and once a survey is finished, the asset has to be registered and uploaded once into the data plane of the EDC. The data has to be put into a storage, and with the help of a self-description creator, we can upload self-descriptions into the federated catalog. Moreover, we need some kind of GUI to browse the data from the catalog, so there is a marketplace or the XFSE portal or the metadata search. So a data consumer is able to browse the data from the catalog with the help of the metadata search, for example, and then initiate a download of survey results. After this, both EDCs need to do a contract negotiation, and if this is successful, the data transfer can be executed from one EDC to the other one, and the data asset can be put into the storage. What is a self-description? When talking about a GaiaX-based ecosystem, we want to have a kind of unified format which is based on standards and is interoperable and portable. So the main goal is to easily transfer data within one ecosystem and even among several ecosystems. A self-description is a major concept to describe metadata of single entities like participants, service offerings, and resources as defined in the GaiaX Trust Framework. A self-description is basically a W3C verifiable presentation which is holding verifiable credentials. You might heard of verifiable credentials when talking about wallets, because they are able to store credentials like this. Every verifiable credential holds a credential subject which encapsulates claims, and those claims are exact the metadata that we want to offer in a federated catalog. So how to create claims? For this we can use the self-description creation wizard I will show you afterwards, which is creating claims in JSON LD format. And what we want to do is to pack these claims into the self-description creator, which creates self-descriptions out of those claims. Moreover, the self-description creator is able to upload the created self-description into the federated catalog. To create a valid self-description, we need claims. So what we can see here are claims describing a survey result data offering, having several attributes and assigned values to it. For example, we can see the belongs to field, which points us to the initial survey service offering. We created that JSON LD file with the help of the self-description creation wizard. For this, we uploaded the shackle shape of the survey result data offering and filled this form with the respective data. After saving this form, we get this JSON LD file, which we can take over to our self-description creator to create a self-description. This application offers two endpoints, and the one I'm showing right now is the create self-description endpoint, which takes the claims as a parameter and generates a self-description. Once we receive our result, which can be seen here, we can see the self-description, of course, having an ID. It's of type verifiable presentation and holds a verifiable credential. Inside, we can find the credential subject, which holds our claims that we just uploaded into this tool. Of course, the credential object is proved, so it can be checked for compliance. And the verifiable presentation is also proved. The survey tool uses the second endpoint, which also generates a self-description. And in addition to that, it uploads the self-description to the federated catalog. Now we have seen how to create self-descriptions and upload them into the federated catalog. I will now show you how to browse this data with the help of a GUI. For this example, I will take the metadata search, which was implemented in our project. For the future, we are planning to extend the XFSE portal with that functionality, but this is still in progress, so I will take the metadata search as an example. Let's zoom in here a little bit. A participant is able to manage self-descriptions, which means he is able to upload self-descriptions into the federated catalog, which then stores them in a database. This database is a graph database, which means that we are able to establish connections between self-descriptions or even other data. The advantage of this is that it's easily possible to visualize this kind of connections between the data within a GUI, for example, the metadata search. Moreover, the user is able to upload schema definitions to the federated catalog, which means that all self-descriptions which are uploaded into the federated catalog are checked against those schemas to only have valid data in the federated catalog. Last but not least, the user is able to use the GUI to search and find data from the federated catalog. What we can see here is our tool metadata search, which acts as a front end from the federated catalog. So the catalog exposes interfaces which are called by the front end, and the data is then visualized. Other front ends could be the XFSE portal, which we are extending with that functionality at the moment, or a marketplace. So having a front end like this, a user wants to be able to browse the catalog for surveys he wants to participate in, or he wants to find closed surveys and get the survey results. He also may find surveys he already participated in, or surveys or result offerings with regards to survey questions and topics, or surveys that have specific participants or a participant count. In our case, we want to find a specific survey result, and that is possible with the help of the metadata search. So for this, we're gonna select our resource, which will be a survey result. And with the search button, we can browse the results of this. And now we are going to pick the latest survey which was created a few minutes ago, which is this one ending with ETW. Let's keep this in mind. And now we can browse the detail page showing all the informations and attributes we entered in our claim, and also the related resource to our initial service offering. Now we are able to download this data, and how this works I will show you in the next slides. Let's come back to the user perspective. The metadata search is able to access the federated catalog to display all the metadata stored there. A supply chain participant wants to be able to use that metadata search and filter and search for survey results. Once he has found something suitable, he wants to be able to initiate a download of survey results out from the metadata search. This should initiate the data transfer from the provider EDC to the participant's EDC or the consumer EDC. And how this works, I will show you right after this. What is an EDC? EDC stands for Eclipse Database Connector. And we are using this tool to establish a secure peer-to-peer transfer. Every EDC has contracts, assets, and policies. So a contract would link the contract definition, the asset ID, and the policy ID together. An asset would be, in our case, the survey result metadata and a link to the data itself. And policies are sets of accessibility rules to have some kind of governance. For data transfer, you always need two EDCs, one on the provider side and one on the consumer side. Both EDC need to do a contract negotiation, and once there is an agreement, the transfer can be initiated from one EDC to the other one. Let's start with the EDC workflow on a really high level. The user chooses an asset in the metadata search. Within the metadata search, he will be able to negotiate a contract to get an agreement, and then the metadata search will initiate the transfer within the EDC by calling a specific interface. So how does the metadata search know which EDC to contact? In our intermediate solution that we are presenting here in our demonstrator, we are including the EDC endpoint URL and the contract ID in the self-description stored in the federated catalog. Our final solution will extract these two technical information from the self-description and put it into a technical self-description containing the EDC endpoint, the contract ID, and the link to the functional self-description, which is also stored in the federated catalog. And with the help of the graph database, which is used in the federated catalog, it's easy to look up both of that self-description once you find one. So after a transfer is initiated within the EDC, a contract is created, linking ID, asset, and policy together. After this, the data asset is read from the storage and transferred to the consumer EDC and put into the configured storage of that EDC consumer. Moreover, we will be able to see a log entry in the transfer history of the consumer EDC. Moreover, the source EDC will also call the EDC blockchain extension, which is deployed inside the EDC, which will write some hash information on the blockchain and the assets that were transferred into the IPFS. Let's go back to our demonstration and the metadata search. We can see that our survey result has an attribute contract ID which is ending with ETW. Let's keep this in mind. We also have two EDCs running in our Kubernetes cluster. So this is the dashboard of the first EDC, and this is the dashboard of the second EDC, which is our target EDC. As we can see, we have an empty transfer history. Coming back to the first EDC, let's browse the assets, and we can find an ETW ending asset here, as well as a Bullwhip policy, which also was created by closing the survey in the survey tool. Also, the contract definition, which we are showing right now and is ending with ETW, was also created by closing the survey and links the policies and the assets together. So now if we have a look into our target EDC, we can browse our volume claim, which is called transfer in our second EDC, and we can see that the directory currently is empty. After the transfer, we would expect a file inside here. And this is what we are going to do now. So by clicking that contract and download button, a contract agreement call will be established from the metadata search to the EDC. And once the agreement is settled, the transfer will be initiated by the metadata search. And once the transfer is executed, we'll be able to find our survey result in that transfer directory. So the transfer was successful. We will also be able to browse the transfer history of the target EDC, and we'll see that our transfer was completed and successful. For the future, we are planning to enable Azure storages instead of volume claims, which will make us more interoperable. So, and now I will hand over back to Philipp, who will show us how the data looks like.
Thank you, Robert, for explaining the GAIA's infrastructure behind the use case. Let's now look at some exemplary survey results from the viewpoint of an OEM. After the download of the results, we're now looking into the results of the survey from the point of view of an OEM. For the presentation within the demo, we transformed the raw survey output to an Excel sheet and added a diagram for better visualization. Later on, dashboards can emerge that would automatically update with the most up-to-date information after each survey cycle. We can see the average results for two questions from the semiconductor and OEM survey respectively. The first question in green in the top left is from the semiconductor survey about the development of demand for radar transceivers. We can see a strong increase from October 2023 to January 2024 with a decline afterwards. The second question from the semiconductor survey in brown on the top right is about the share of automotive business distributed across the world regions. On the bottom in purple, we can see the results from the OEM about the development of the light vehicle market, as well as their share of automotive business across the world regions in blue. To better compare the demand for light vehicles and radar transceivers, we can look into a diagram. We can see that the OEMs expect a strong growth of the light vehicle demand in the upcoming 4 months, with a less steep growth afterwards. This can be seen as the purple line. In contrary, the semiconductor manufacturers expect a similar development for the radar transceivers, although a weaker growth overall. This information can now be used for the further planning of our own production. We are now finished with our demonstrator and come to a small conclusion and summary of our use case. A true demand ecosystem of more accurate sharing of demand and inventory information will help us to mitigate the bullwhip effect in automotive supply chains sustainably. Future shortages in automotive, as seen during COVID-19, can then be mitigated more effectively. Also, GAIA-X and its core technologies enables the emerging of such information sharing ecosystems across supply chains. And finally, future mobility, including electric vehicles, automated driving, smart cities, and the decarbonization of automotive is enabled by reliable supply of semiconductors. Thank you very much for your attention. If you have further questions, you can contact me or Robert by using the email addresses you can find here on the slide.